let's determine cube root of I. So we want to determine a complex number z such that z cube equal to I. Observe that if z square equal to 1, then we get z equal to 1 comma minus 1. What if z cube equal to 1? If we restrict ourselves to only real number, then we say that z equal to 1. But if we restrict ourselves to complex number as well, or if we consider complex number as well, then we get z equal to 1 omega square, where omega is the complex cube root of unity, and omega equal to minus 1 plus minus root 3I by 2. Whether you take positive root or negative root, it is up to you, but omega can be one of those. Now how about the equation z cube equal to I, or we want to determine a complex number z such that cube root of I equal to z. Once again, we want to determine a complex number z such that cube root of I equal to z. That is, z must be equal to I to the power 1/3. Now of course we can do it by letting z equal to x plus iy, but it will be easier if we use Euler's theorem, or rather de Moivre's theorem. So we want to solve the equation z cube equal to I. Let's take modulus on both sides to say that modulus of z cube equal to modulus of I. Once again, modulus of z cube must be equal to modulus of I, but modulus of z cube is simply equal to mod z whole thing cube, and modulus of I equal to 0 plus 1 times I. So modulus of I equal to square root of real part square plus imaginary part square, which is exactly equal to 1. Is a real number. Modulus of a complex number is a real number. So modulus of z cube is equal to 1. So mod z equal to 1, because mod z is a real number. Now obvious question is, what do you think polar form of complex number will be? Well, any complex number can be written in the expression r cos theta plus I sin theta. Once again, we can write a complex number in that expression r cos theta plus I sin theta, and we call this to be polar form of the complex number, and r is the modulus of complex number, and modulus of complex number turns out to be 1. So we can write z equal to cos theta plus I sin theta. Let's write it in equation 1. By equation 1, cos theta plus I sin theta, cos theta plus I sin theta to the power 3 equal to I, or cos theta plus I sin theta, cos theta plus I sin theta equal to I to the power 1/3, I to the power 1/3. As we said, we want to apply de Moivre's theorem. I can be written as 0 plus 1i. It can also be written in the form of polar form, and that's equal to cos pi by 2 plus I sin pi by 2. Cos pi by 2 plus I sin pi by 2. To the power 1/3, we write it as it is. Okay, so far we got cos theta plus I sin theta equal to cos pi by 2 plus I sin pi by 2 to the power 1/3. Now by de Moivre's theorem, let's recall de Moivre's theorem. By de Moivre's theorem, cos theta plus I sin theta to the power n equal to cos n theta plus I sin n theta, where n can be any real number. We choose n equal to 1/3. So we can write left hand side let's copy as it is, cos theta plus I sin theta, z equal to cos theta plus I sin theta, and we want to find such a complex number z equal to cos pi by 2 plus I sin pi by 2. As we said, we can multiply by power by n, in this case n equal to 1/3. So 1/3 of pi by 2, 1/3 of pi by 2. That's cos pi by 6, that's cos 60 degree, sorry, 30 degree. Cos 30 degree is root 3 by 2, and sin 30 degree is 1 by 2. So it turns out that cube root of I equal to is equal to root 3 by 2 plus I by 2. Now let's look at the thing what we did so far. We wrote z square equal to 1 and we wrote z equal to plus minus 1. We wrote z cube equal to 1 and we solved it and say that as long as if we fix z to be a real number, there is only one answer, and if we allow z to be a complex number, then we get 3 number of answer. Can we do similar things here? The answer is yes. You see that cube root of I equal to root 3 by 2 plus I by 2, that's we call it principal value, but there are other value as well. How? Let's see how. You see that if I add 360 degree or 2n pi, cos theta do not change. Similarly, if I add 360 degree or 2n pi, sin theta also do not change. So I can add 2n pi and I get the same expression. Once again, I can add 2n pi to pi by 2 plus 2n pi. I can add pi by 2 plus 2n pi and say that we are still valid, or our work is valid. Next, when we choose n equal to 0, then we get cube root of I equal to root 3 by 2 plus I by 2. That's the principal value of cube root of I equal to root 3 by 2 plus I by 2. Are there other values? The answer is yes. When I take n equal to 1, for n equal to 1, we got 90 degree plus 360 degree. If we divide by 3, we get 90 by 2 by 3 is 30 degree, and 360 degree by 3 is 120 degree. So we get cos 150 degree plus I sin 150 degree. So for n equal to 1, cube root of I equal to cos 150 degree plus I sin 150 degree. Cos 150 degree is negative, so minus root 3 by 2, and sin 150 degree is positive, and that's equal to sin 30 degree, and that's equal to 1 by 2. For n equal to 2, we get cube root of I equal to 1/3 of 90 degree plus 2 times 360 degree, and if you divide 360 degree by 3, we get 120 degree, 240 degree, and 90 plus 240, 90, 1/3 of 90 is 30, 30 plus 240 is 270 degree, and cos 270 degree equal to 0, and then sin 270 degree equal to minus of sin 90 degree, so we get minus I. So cube root of I is simply equal to minus I. So we got 1 root, 2 root, and 3 root. So we conclude that principal value of cube root of I is simply equal to root 3 by 2 plus I by 2. There are other value of cube root of I as well, and those are cube root of I is also equal to minus root 3 by 2 plus I by 2, minus root 3 by 2 plus I by 2, and cube root of I is also equal to minus I. So the final answer is root 3 by 2 plus I by 2 if we are talking only the principal value, and then minus root 3 by 2 plus I by 2, and then lastly minus I.